Hello, my friends. Welcome back. This is Dr. Mohamed Nezami with the last presentation on the special topic of radial power combiners or splitters. Now, again, we have been covering radial combiners that are appropriate for use in phased array antennas and power amplifiers, specifically for 5G broadcasting, radars, and SATCOMs, both ground station and transponders as well. The playlist here contains, this will be the 6th video. You can go ahead and look at that. We've started way back at the, looking at the substrate integrated waveguide, radial combiners, all the way until we covered the 2 sessions on the use of oversized coaxial cavity with the feeding a coaxial line feeding a ring cavity. We've covered that one of those last time that uses SMA disk-loaded probes for peripheral outputs or inputs in the case of in the situation of combining. And now today we're going to cover the same concept, except we're going to replace the microstrip. I mean the coaxial disk-loaded probe to a microstrip one, and purposely because we really, when we use these radial combiners, we use them in conjunction with other parts of the system, be it whether they are connected to an antenna array, printed batches, or just a parallel structure of power amplifiers. In either case, the transition from the cavity onto these systems is usually done using printed planar circuitry, which is microstrip and strip lines and suspended lines. So, all right. So again, my name is Mohamed Nezami, Dr. Mohamed Nezami. I specialize in RF and microwave circuit and design for circuits and systems. I am an independent contractor. I operate right now out of Jordan with many years experience in United States and Europe and Asia as well. So if you have any need for any opportunities to help you with any of your designs as a contractor, please reach out to me at this number here using these apps or directly dialing this number or the email that is highlighted right here. Now, also, meanwhile, I'm going to be holding a 3-day training on designing RF and microwave devices using HFSS, the 3D modeling, okay? And this workshop will be basically hands-on. Everybody's going to have their own laptop equipped with an evaluation copy or your own copy of HFSS. And we will sit down and throughout 3 days, we will be designing hands-on in a team, all of the devices that you will see in my videos, not just this playlist, but all the way from basic splitters to circular polarized antennas, okay? So the first session will be done on the February 15th to 18th, okay, this year. And it's going to be held in Jerash, Jordan, at this site here. The price is shown right here, and that includes the room and meals as well. So you can review the videos on this channel here, okay? And if you like what you see, please, if you want to register, please let me know. So email me your name and your information, and I will guide you through the registration. Following on to that, that training, that I will hold other sessions as well using the RF Pro from Keysight ADS And then we will also be working closely with PCB designs with using Cadence Allegro, okay? And basically in there, we will be doing a lot of post layout verification using both ANSYS and ADS or RF Pro in order to validate the circuitry that has been laid out ready to go to production. All right, let's just as a reminder, I know last time and even the video before, the last video and the video before that, I have showed the justification. Why would you want to go and build RF radial combiners or splitters as opposed to building them in planar, okay? And the reason was simply is because if you have a very wide bandwidth, that's one thing. And if you have many branches to cover, that's the output, the peripherals are say more than 8, then the losses are going to be too much and the mismatches between the channels will be too much that it justifies using radial combiners because they're based on basically combining signals in space, so they don't actually propagate through copper or substrate, so they're not subjected to copper losses or metal losses or dielectric tangent dielectric losses, okay? So basically, like I stated here, in the case of power amplifiers, really the power amplifier itself, if it's within the if it's built embedded into a radial splitter and radial combiner, it becomes as what we call active integrated antenna, okay? Because that's what it is really. So let's look at a conventional combining network where we are using actually Wilkinson or 90-degree hybrid or 180-degree hybrid, whatever, to split your signals and come into the amplifiers, and then you're gonna combine again through all these stages. Like in this case, there's T stages of combining. You can see that the losses are tremendous and they accumulate, okay? Plus the mismatches, you know, you're always going to get mismatches between these, whereas in radial combiners or splitters, you really don't have mismatches because the signal is completely coherently divided or summed up in space using symmetrical cavity and symmetrical feeds, and the peripherals are distributed symmetrically and such that you won't get any asymmetries between the outputs. So this is a nice diagram that I got. Where's the reference? I think this is from the IEEE MTT Delicio or somebody else that based it on that. Okay, so what this shows a comparison between if you have a combiner that is lossless, okay, radial combiner, whatever power you put in, okay, whatever the number of channels that you have, you're always going to just basically sum up the signal with exactly that number multiplying by that number, meaning if you have 2 signals, you're going to get twice. If you have 3 signals, you get 3, and so forth. So if you have a loss, if you introduce the little loss, like in this case, add a little loss, so say 1 dB of spatial combiner loss, then you just bring that line downward by 1 dB, and that's what you're going to get, basically, linear. And there is no diminishing point of return on the number of elements that you would have beyond, say, all the way you can go, and the signal will just keep going linearly. Now, unlike that, if you have a corporate combining like this, okay, what happens in here, this graph shows if you have, if these combiners and splitters in the cases where you have 0.1 dB or 0.2 dB or 0.3 dB or 0.4 dB of combining or splitting loss, look what happened. What happens is that you're going to get a curve that beyond a certain point, it becomes useless to use these combiners. So for instance, if you have a 0.4 dB loss, which is typical in a lot of cases, on some of the cheap substrates for a Wilkinson divider, you let's say that if the point where you depart from a radial combiner is this point here. Is you can see that you're linear up to say 1, 2, 3, 4, 5, 6, 7 elements, 7 splittings. Beyond that, just the losses will just tremendously reduce the signal level. And likewise, if you have it becomes less of a point and 0.1, but even still, if you have a 0.1 dB, which is very excellent to have, that would be a very well-designed splitter on very expensive substrate. You're only going to get, say, 15 or 16 numbers on the peripheral ports, where beyond that, if you add more outputs, or you combine more outputs, you're gonna basically start off the cliff. So this here, plus the reasons I showed you last time, where, for instance, these Wilkinson dividers and combiners, regardless of whether they're Wilkinson or 90-degree hybrid or 180-degree hybrid, they're all based on a quarter wavelength section. And if you want to broadband that, you have to use multi-sections, and then it becomes tremendously large in order to cover. And then beyond a certain point, you start getting into these issues here, where the accumulated losses makes it useless to do that using it that way. Okay? So today, we're going to cover one last example of radial combiners. And what it is similar to the last video, same exact one, except for different frequency this time. We've got a coaxial line feed at this point, SMA or N-type. We come in, and then we have a tapered coaxial line, which has a diameter oversized to fit the probes. And the probes are this time, not unlike last video. Last video they were coaxial metal probes where you extended the inner conductor out and loaded it with a little disc, and that would be your basically waveguide to a coaxial line transition. In this case, we slide in a bunch of probes that are on a small piece of substrate, okay? And so as you can see here, this is the gap, the air gap between the inner and outer, and you can see how it comes down. And there's the disc. The disc is the widening, the horizontal widening from the tapered line, okay? And that's where we insert around 32 probes, okay? So just so we can show that better, let's go to HFSS, and this is the system. So basically we come in here, we feed the signal on this disk here, okay? Okay, and this disk here is basically a top cap, metal cap that basically there's this brick of aluminum in here, and this brick of aluminum has a hollow cone in it where the inner conductor comes in. Okay, we start out with a small piece of extending the N-type inner conductor in here, and then we go out and taper and match the impedance, the parallel impedance that is this line here. This is, of course, this is a line here where the tapering is all the way from 50 to this point here, and this is a coaxial line in here, except it's not tapered, it's fixed. So, and I believe this one is probably 30 ohms, which means that If this is 30, then that means the probes are 30 times 32. Okay. And then the probes are basically, this is the probe. It's just a little microstrip antenna connected to a feed line, and that comes off the bottom. I'll show you in a minute. Okay. You can see it right there. So you can see how this is it. So there's an opening, okay, in here where the substrate goes in, and then basically a small piece of 50 ohm line, that's the 50 ohm line, and then a narrow line, and then the strip, the rectangular batch in there that picks up the signal. Okay. So now again, so let's look at this again. So if you look at this is the cone that represents the okay, let's see, we need to grab the not the probe, but the okay, let's see what that line is. Okay, here it is. Okay, so we need to have these guys. So feed in, okay, this one, and then this one. Okay, so now if we zoom in on that, that's basically our, as you can see, that's the inner connector, inner conductor of the coaxial line, starting from 50 ohm, tapering to this impedance here that goes out linearly, and that's a transformer basically to match the impedance of this line in here that is basically matching to the 32 times the parallel combination of 32 probes around the system. Okay, so let's get back to the session. Okay, now the of course the coaxial connector, when we feed the cap in here with a wave port, basically the E field distributed symmetrically and equally 360 degrees apart, around. And that's really what offers the key to the symmetry and the good matching between all the peripheral ports. Okay, of course, alongside in the axial, in the outer, alongside the inner conductor, this is what you're going to get. You're going to get an E field that distributes like this, of course, and it will be symmetrical every half wavelength. So let's go back to the this one. So if we look at the let's flip it. Okay, if we look at the E field on this, and I'll show you in a minute when we run this. So you can see that the wave, I've excited the wave in here, and the wave propagates, and you can see the color coded, and this according to the strength of the signal. As you go down and down, the signal gets less and less because it gets divided into 32 symmetrical parts. So you can see that where the half wavelength symmetry is coming in alongside the cone that comes in, and then you can see it also at the bottom. If you look at the bottom, you look at how symmetrical this is, or close to it. Okay, so that the signal is, well, this is from top really, but this is going down the cone. Let's look at the okay, this is the bottom. Okay, so if you can see the bottom, look at how symmetrical this is. Okay, we come down, the signal comes down all the way, and it goes into the probes equally, splitting on all of these. Okay, so you can see how well this is balanced. Okay, all right, so oh, now the so somebody might come in and say, well, how do you design the cone? You know, we know that we have, first of all, the first thing that you want to do is you want to have the bottom in here, okay, the bottom, which is the cone, and this is here is plotted as a microstrip, but regardless, this is just showing the impedance profile, because the width in here, as you can see here, the width in here is for 50 ohm and the width in here is 25 ohm, so this is wider than this, and in between you can go either linear or you can give Klopfenstein, Tabor transformer, or you can do Dolph Chebyshev Tabor. Okay, these you can reach out to me if you want to know more about, but they're just type these two keywords, these few keywords on Google, and you'll get a lot of theory of operations and methods of designing these and build up background. And especially from this website here, they have these nice fellows here. They posted a lot of calculators. One of the calculators is actually to do the Klopfenstein Tabor transformer, in which, of course, now back then these guys did it a few years before ADS and AWR included a built-in a synthesizer for the Tabor line. So you can do this with you don't have to use a spreadsheet calculator that you get from this site. There are also MATLAB has on their website, you can go to the public area of MATLAB site, and you can download a lot of people posted MATLAB code that synthesizes these for microstrip. But then to do it for the coaxial line, all you have to do is just you're getting the impedance, so you can come in and find out what B to A has to be, where B is the inner, and I mean A is the inner and B is the outer diameter or radius, whichever way, because it's a ratio. Whether you use radius or diameter, it cancels out. It comes up to the same answer. So you can use that. Now that gives you a ratio, but how do you find the outer width then? Well, you find it based on how much room do you need to fit in your these things. Like in this case, for instance, you have the number of these, and you have how much spacing you want between them, and then you know physically what kind of size you need in here. In a lot of cases, this turns out to be somewhere around, say, 5 to 7, 8 inches, okay, which is 10 centimeters, maybe roughly. So then you know exactly what the outer radius has to be. So that automatically gives you the profile for the inner, and therefore you get a mapping, a profile plot that shows the distance versus the impedance as it gradually matches the 50 ohm to this side here. This side is here, is where, of course, you're basically loaded with the parallel combination of all the probes. So here's this is these are the probes. I just showed them. I hide the rest of the system, and we can show only the probes in here. Okay. There is a publication. Okay, so this system here, let's see. So this system in here was done for the U-band. So this is good anywhere between 36 to 45 or 35 to 45 gigahertz. Okay. And I could do better on the Rebel in here. There are some issues with the limitation on number of meshes that I can run right now. So this is what all I can get, but you can get better than this even, okay? So let's get back to, okay, so we showed this. We showed how the power is picked up by the, okay, there is a publication that is based on very much the same thing, except I modified it, and I found an error in this one here. There is an error There is, so this is one generic diagram of how this system look like, okay? So basically you have a coaxial connector in here. The inner comes in and feeds the cone or the taper line, okay? And then you have the other line, the inline, load line. And then of course you got the disc cavity where all the probes come in. And when I looked at this, I realized they left out the ground in here. There's a ground that should be on the substrate in here. There's a ground piece right here that goes in underneath the probe, because the probe in here, there is no ground plane. But as soon as it gets to here, that's where the 50 ohm starts. This is the ground on the back that is underneath this area here. Okay, this area here needs a ground. This is not suspended line. This is a microstrip line, so it needs ground below it. And unfortunately, in this one, they extended the probe feed line all the way to here, and this is without ground. It's floating right now. This is a mistake. So if some of you guys, it's a little bit older. It's about 10 years or so publication. But if you can, they may have drawn it and left it out because that's not. So okay, well, before we get that, so let's look at the overall parameters that you would have to use in your HFS system. We know that the this here, twice of the inner radius, and then the radius in here, these are given because we know that it's commercially off-the-shelf connector, so we know exactly what it has to be. And then now you can design all of these parameters. So we've got all these radiuses, okay? All these radiuses. We've got these lengths in here, and then we've got dimensions for the probe itself, okay? So we've got the length of the probe, okay? And then we've got the width of the probe, okay, and the height of the probe. We've got the length of the matching section, water wave matching section, with this impedance, okay? And so therefore you can put all of this in HFSS, and that's really what I did, except I basically terminated this to this point. I did not extend, I got rid of this, and then I just stopped right here, because that's justified, because you're interested in just the splitter without any additional extension. So where would you use this? This is exactly where you would use it, like we've been showing. So you use one of the splitters on the split side on the input, okay, and then you basically the probes comes in, and these will be individual 32 individual RF amplifier cards that you plug in all around the system, and of course you have to assemble it and assemble the heat sink as well, and so forth. And this becomes like a little tube that, and this would be a radial array power amplifier made of 32 elements. And of course, your DC comes in here or on this side, okay? Now, this is a picture from that publication, which I will show you in a minute where that publication is. I'll give you the name of it, but this shows how they did, after they did it, how they tested it back to back. So and this is usually what you do. When you design one of these, you build two of them and you put them back to back, and then it's easier that way instead of going in and having, because how would you test this side using a network analyzer? You know, obviously you would have to attach edge mountable connectors, SMA connectors, and that's, you've added more stuff, and you can't really get very much a close look at the actual losses and impairments of the part itself. So the best way to do it is, since it's symmetrical and repeatable, you just build two, put them back to back, and that way you only have two port device, input and output. That's it. Okay. Now, unless of course you wanna, if you're not convinced with the 3 modeling results that you can get, you can go to individually all these ports and start building basically fixture assembly to look closer and analyze the signal coming from every port individually. Okay, so this is after it's assembled. All right. So again, so by this we have really covered all of the aspects of radial splitters and connectors, which I really wanted to show you. And we've used all these designs to show how this system is constructed. This was the board. These boards were done on Doroid 5880, by the way, just in case. Okay, so let's go. I want to show you let's show you the publication. Okay, it's this one. Yeah, this is the publication in here. Basically, it's a compact 32-way cavity by Song. And I know this gentleman here has a bunch of these papers on this on radial combiners. Okay, so you can see it here, and I hope if he watches this video to point that out to him that there is a missing ground in this one here, this side. There should be a ground on this and on this. Either that or they have to just chop it off right here and attach the ports to it. The ports on the port excitement of this, basically, just in case if some of you interested, this is basically what we do. So this is one excitement in here, which is a wave port done on this enclosure on this end. Okay, and then the peripheral ones, we just basically here they are. So I created a sheet, and the sheet basically has a wave port to it as well. Okay, the sheet on the peripherals. Every one of those peripherals, they have a sheet that basically it's a cap to the bottom opening in the disc cavity. So every one of these ones, as you can see here, so as you can see, everyone has cover sheet which I associated with it a wave port. Okay. So this is it, my friends. So next present week, I will show you another presentation. So until I see you until next week, I hope you have fun. Please go back to my videos. There's now close to 25 videos that I have posted, and you can look at these. And please consider coming to my training, which will be held, show you, which will be held in February. That is right here. So if you come to my training, I'm hoping that if you have just a basic knowledge and use of HFSS, that you will get a lot of knowledge and hands-on experience. And this is targeted for people in the Middle East area. I welcome people from Saudi, from United Arab Emirates, from Egypt, from Lebanon, or Turkey. Of course, we know that there's a lot of high frequency industry in Turkey, so, and it's close next door. Hopefully people come in and we're going to enjoy a 3-day of work together, and you're going to everyone will get his I will work with ANSYS to accommodate an evaluation copy of the software to be loaded onto every laptop that with every trainee that comes in. You will go out with the slides, with the source files of all these videos that I've showed you, all these designs. You will have these, and you will have my copy, and you'll have your own copy, because you're going to build them. We're going to come in and you're going to be trained. You're going to sit and one-on-one until you, and we will customize it as well. So we will survey the audience, the registered individuals. We will see which areas they are interested mostly in, where what is relevant to the work they're doing, and shift it so that we can focus on those areas. Okay. Until then, I appreciate it. This is Dr. Mohamed Nezami. Thank you very much for attending, and watching this, please press like and share it if you would with your friends and colleagues. Thank you very much.